All right, class, here we go. Here's some more frictional notes for us. Again, just remember that static and kinetic friction depend on two factors. The first was the type of surfaces that are in contact, which is represented by the mu value. And then the other is the normal force, which is the F sub n value from yesterday. And again, these forces are independent of the area of in contact and the speed of the sliding motion. Air drag, on the other hand, increases as speed increases, but we're not taking air drag into consideration as a force at this point. So let's take a look at this sample problem here, this first one. So we have a 20 kilogram block, which is represented here. It's on a horizontal surface, and we're given the coefficient of static and kinetic friction. We want to know what the force is required to set the block in motion. So basically, I need to overcome static friction with that. So I'm looking for the force I'm going to be applying here, and I'm also looking at the amount of static friction that can be supplied by the surfaces in contact there. Here's my equation. Again, I need to know the normal force. It's equal to the weight of the block because the net force is 0. So the normal force and the weight are equal. And so I can substitute for normal force is weight, which is mg. You can see that substitution there. And then I can just substitute my numbers and solve and get 98 newtons as my static friction. So therefore, I need to have 98 newtons of force to overcome that. Now, the second one, we are now applying 120 newtons acting on the block once it's set into motion, and we want to find the acceleration of the block. Here's our force in the direction of motion. Here's our force that's opposing motion. And our acceleration is the net force over the mass. Remember, that's Newton's second law, so we have to look at what is the net force. It is the forces in the direction of motion minus the forces opposing motion. So that's what I'm getting at here. And we can plug that in. And for Fk, we can plug in mu k Fn. We know the normal force is mg. Solve for the kinetic friction. Substitute it back in. Do our subtraction here, and now this is our net force acting on the block, which is 77 newtons in the direction of motion. We then can plug it into this equation here. We know the mass. 2 digits, 3 digits. Answer then has 2 digits. Another note is on the addition-subtraction rule here. Again, good to the ones digit, good to the 10th. So our answer is only good to the ones digit. Again, if you need to pause for a minute and write this information down, you can. I think that's pretty straightforward in terms of how that was solved for. Look at our second example. We have 125 Newton force acting on a 15 kilogram block. It's now sliding at a constant velocity. We're determining the coefficient of kinetic friction. So we're looking for mu k in this one. So if we're solving for mu k, it's Fk over Fn. How do we find the sliding friction? Well, how is it moving? Constant velocity. So that should tell us something about the acceleration. It's 0. So therefore, the net force is 0, and the forces in the direction of motion equal the forces opposing motion. So therefore, Fk equals 125 newtons. And now we just need to find the normal force, which in this case it's 15 kilograms, is the weight or the mass. So we can find the weight, and the normal force is equal to the weight, which is mg. So the normal force is right there. Substitute it in, and we get a mu k value of 0.850. Good example 3. A 350 Newton force acts on a 50 kilogram block, and now it's accelerating. So if it's accelerating, we know that it has a what? A net force. So again, we can't say that the net force is 0 here. So if you look at my arrows here, you can see that the force in the direction of motion is greater than the force of sliding friction. And how much greater is it? Well, it's net force greater. So again, show our free body diagram, and now we can find a few of the items that are here. Net forces, or the normal force, is equal to the weight. So we can solve for that. That goes into our equation. And now here's the harder part. The net force is equal to the force in the direction of motion minus the force opposing motion. And we need to solve for F sub k. When we know the net force is mass times acceleration. Here's the acceleration, here's our mass. And solving for Fk, we just, again, move Fk to the other side, move ma back over to here. This is how we get this equation here. Substitute. Show our addition rule. Good to the ones, good to the 10th. Our answer is only good to the ones digit. Now we have both our Fk value and our Fn value, which can then be plugged into here. And we can solve for our mu k. And one more example for you. Last example. So we have a boy on a sled. He's coasting at 4 meters per second along a horizontal stretch of snow. The sled has a mass of 13 kilograms. The boy has a mass of 25 kilograms. And the coefficient of kinetic friction is 0.05 between the sled and the snow. How far will the sled travel before coming to a halt? A little different problem. Think of it this way. If you're sitting at a desk at home, go ahead and push your book across the desk. If it's coasting, that means there's no force acting behind it. So as soon as your hand leaves the book, what's the only force that's acting on it? The friction between the book and the desk. So here, the only force that's acting on him is going to be his kinetic friction. We know the mu k value. We can find the normal force based on his mass and the sled's mass. We can find the weight of both of those. And then if we know the force, that will be the net force. And if we know the net force, we can find the acceleration. If we know the acceleration, we can then, and the initial velocity, we can then find the distance traveled. So that's kind of what we're going to be going through here. So a few things. Here's the distance traveled that we're looking for. It's going to be Vf squared minus Vo squared over 2a. Vf is 0, so that cancels out. Acceleration, we need to find that based on the net force. So here we go. The net force, force in the direction of motion minus forces opposing motion. What did we say this force in the direction of motion was? It's 0. He's no longer being pushed, he's coasting. The force opposing motion is the kinetic friction. So if we look at this, this will cancel to just negative Fk. And we find Fk, UKFN. Again, we talked about it in the beginning. UK is right here. Fn, we can use the weight of both the sled and the boy. There we go. Mass of the sled and the boy times g. There's the normal force. Plug it into here. Find our coefficient of, or our kinetic friction. And now we can substitute that in to find the net force. And again, it should be a negative value because what is it doing? This object is starting with a 4 meters per second velocity and it's slowing down. And that force is opposing motion. So it should be, if this is a positive 4 going in this direction, this has to be a negative force to slow it down. If that's the net force, we know the mass of the system. We can find its acceleration, again, a negative acceleration. And if we plug into this equation, you can see now that the final velocity is 0, the initial velocity is 4 meters per second, and the acceleration now is this value, so we can go back to our kinematics equations and solve. So it will come to a halt after 16.3 meters of travel. So hopefully that gets you started on the problems on the back. Again, good things to think about here. And again, we'll have some discussion on Monday about these problems, because again, you're probably going to struggle a little bit with number 6. That's a tough one, but give it a shot. And then again, give the bonuses a try. They're a little bit more difficult as well, but I think definitely doable based on the skills you have and know. So have a great weekend and enjoy your Friday.